ECE-23 Performance Task Number 11 by Raymond Lorca, BS-ECE-3A. Non-orthogonal multiple access. Non-orthogonal multiple access, or NOMA, is one of the most promising radio access techniques in next-generation wireless communication. Compared to orthogonal frequency division multiple access, or OFDMA, which is the current de facto standard orthogonal multiple access, or OMA technique. NOMA offers a set of desirable potential benefits such as enhanced spectrum efficiency, reduced latency with high reliability, and massive connectivity. The baseline idea of NOMA is to serve multiple users using the same resource in terms of time, frequency, and space. Major category of NOMA techniques are power domain NOMA and code domain NOMA. Code domain NOMA, or the code domain NOMA, multiplexes the users by employing specific spreading sequences for each user, which has sparse, low density, and low intercorrelation properties. In recent developments in the 5G technologies, SCMA is considered the most efficient method due to its lower complexity levels. The power domain NOMA, or in PD NOMA, or power domain NOMA, multiplexing is performed in power domain. Signals from different users are superposed at the transmitter by allocating optimal power to each user, and the subsequent signal is then transferred using the same subcarriers. We consider orthogonal frequency division multiplexing, or OFDM, as the modulation scheme, and NOMA as the multiple access scheme. In conventional 4G networks, as natural extension of OFDM, orthogonal frequency division multiple access, or OFDMA, is used where information for each user is assigned to a subset of subcarrier. In NOMA, on the other hand, all of the subcarrier can be used by each user. Okay, spectrum sharing of for OFDM A and NOMA for two users. This illustrates the spectrum sharing for OFDMA and NOMA for two users. The concept applies both uplink and downlink transmission. Superposition coding at the transmitter and successive interference cancellation, or SIC, at the receiver makes it possible to utilize the same spectrum for all users. At the transmitter site, all the individual information signals are superimposed into a single waveform, while at the receiver, SIC decodes the signals one by one until it finds the desired signal. Successive interference cancellation. illustrate the concept. In the illustration, the three information signal indicates with different colors are superimposed at the transmitter. The received signal at the SIC receiver includes all these three signals. The first signal that SIC decodes is the strongest one while the other as interference. The first decode signal is then subtracted from the received signal, and if the decoding is perfect, the waveform with the rest of the signals is accurately obtained. SIC iterates the process until it finds the desired signal. The success of SIC depends on the perfect cancellation of the signals in the iteration steps. The transmitted should accurately split the power between the user information waveform and superimpose them. The methodology for power split differs for uplink and downlink channel. NOMA for downlink. In NOMA downlink, the base station superimposes the information waveforms for its service users. Each user equipment UE employs SIC to detect their own signal. NOMA for downlink. This figure shows a BS and K number of UEs with SIC receivers. In the network, it is assumed that the UE1 is the closest to the base station, and UEK is the farthest. The challenge for BS is to decide how to allocate the power among the individual information waveforms, which is critical for SIC and NOMA downlink. More power is allocated to UE located farther from the BS and the least power to the UE closest to the BS. In the network, all UEs receive the same signal that contain the information for all users. Each UE decodes the strongest signal first and then subtracted the decoded signal from the received signal. SIC receiver iterates the subtraction until it finds its own signal. UE located close to the BS can cancel the signals of the farther UEs. Each since the signal of the farthest UEs contributes the most of the received signal, it will decode its own signal first. NOMA for uplink. This figure depicts a network that multiplexes K UEs in the uplink using NOMA. This time BS employs SIC in order to distinguish the user's signal. That's all. Thank you.